Now I'm going to talk about our second work published at iClear this year. This work was led by our PhD student, Vivor. And in this work, we look into the problem of interpretable machining via feature importance. Given black box models, we aim to learn explainer that offer explanation regarding which word, which feature, which pixel important and crucial for the prediction of a black box model. As you know, in explainable AI, there are two dominating live thinking. The first one is additive approach, in which, given an example, we aim to conduct a local space and local distribution and train linear model to imitate the prediction of black box models on local space. Finally, we rely on the coefficient of linear model to justify important level of feature. The second live thinking relies on information theory, in which we aim to select a subset of features that maximize mutual information with respect to the predicted label. Our work leverages and take advantage of two those line of thinking. We also amortize explainer to be able to benefit from global information and global training. We conducted experiment on a real-world data set and also human evaluation to demonstrate that our approach really outperform the SOTA baseline in three types of data. If you want to know more about our work, please come to our poster. Thanks for your attention.
All right, so I'm talking about multi-rocket, which is some of our recent work in the area of time series classification. So that's where our inputs are time series, values ordered in time, and we want to assign labels to those time series. So for example, we might have audio recordings of passing insects, and we might want to identify their species. So here we're building on some of our earlier work, which concentrated on developing more efficient methods for performing time series classification. And in this work in particular, we want to take that efficient base and try and make it as accurate as possible. And so through a process of extensive experimentation, focusing on, this work focuses on deriving features from convolutional output. So our basic setup is we have input time series, we convolve them with some set of convolutional kernels, we extract features from the convolutional output and then use them to train a linear classifier. So this work focuses on the pooling stage, extracting features from the convolutional output. And after extensive experimentation with sort of every conceivable method of extracting features from convolutional output, we settle on 4 key features. And when we put this all together, so we have our efficient base with these 4 key features, we can more or less match the accuracy of the single most accurate method for time series classification on the key benchmark in this field, but do it approximately 500 times faster. So, thank you.
Okay. I'm Levin. I want to know how the brain works, especially the human brain, and basically current imaging techniques measure things like blood oxygenation changes, or you can use inverse source reconstruction for MEG or EEG data to estimate current source signals at the level of cerebral cortex, but you can't actually image the neurophysiological variables. So this is work by Yun Zhao, who's a PhD student, and he published it in Neuroimage. And so basically we assume that at each cortical location we can approximate the cortical activity with what's called a neural mass model. It's a neural population model which has, basically it's like an artificial neural network, but with temporal dynamics, and it's got population connection strengths that are sort of at the resolution that's affordable with current imaging techniques. And so at each location we have a model, and then that model can be connected up to other regions within the brain, and we basically use specially derived Kalman filters that help us to infer these neurophysiological variables that can't be imaged directly. And so this paper is about creating a new method that gives you a time-resolved way to image brain activity. So there's other inference techniques that are out there that are able to, image things like this, but they're not very scalable, and they don't give you that temporal resolution. So that's what this work is about. And so down the bottom you can see you can do contrast imaging at different time points to see these additional physiological variables, and it just gives you further insight into brain function in order to study things like the resting state, which is what this paper is about, and then other things like changes in the brain due to anesthesia in order to study mechanisms of consciousness. And the other benefit of the temporal resolution is you can, correlate the brain activity or the neurophysiological estimates to behavioural changes or other tasks that individuals are doing while you're doing the imaging. So just gives us a new way to study the brain. Right?
Okay, so there is a bit of a trend today to talk about adversarial examples and adversarial and then brittleness. So we all know that machine learning models require verification, explanation. We really need to understand what is happening inside. Now, the lion's share of explainability approaches in the area of AI is basically, it applies statistical magic. Like we sample in the vicinity of an instance we're looking at, and then we run the classifier, and then we see what the outcomes are, and based on this and based on minimizing some kind of criteria, we get an explanation. Now, we don't have that degree, so we're not wizards. We take on this problem differently. So we consider a computer scientist's approach. What we propose to do is to actually look inside of the model, reason about it formally. So what we need to do is to represent it logically and then apply formal reasoning approaches that exist. There are plenty of them. And then we can see which features are really relevant for this concrete prediction and which features are not relevant for the prediction. Now, in contrast to the black box explainers, this is a difficult problem computationally. So this paper is kind of a survey paper that overviewed our understanding of what we could do with formal methods in the area of XAI in the end of 2021, beginning of 2022. We know that we can explain simple models in polytime, and in general the problem is DP hard. But despite the hardness, we can still, for instance, explain efficiently tree ensembles, but we cannot explain neural networks efficiently. At least we could not at that point. So if you're interested in the area of formal explainable AI, if you really want to understand how we can explain models in such a way that we trust explanations, please talk to me at the poster.
Morning, everyone. So my name is Jie Chen. Also can call me Mike. I'm a PhD student supervised by Daniel and Peter. Today, I'll talk about our recent work on computing high-quality solutions for multi-agent pathfinding problem. So in this problem, we will navigate a team of agents from their start locations to their goal locations. And the problem is critical for real-world applications like warehouse systems. And if you look at a warehouse system, we will find, okay, usually they have thousands of agents, and in a warehouse with kilometers long. And they want compute and replan passes frequently. And also they want solver to return plan fast. But if we look at what we have on the existing market, we will find, okay, we have optimal solvers that can compute optimal solutions. That is great. And we bring them to the warehouse. And how many agents they can navigate? Well, only dozens. Well, we also can find we have suboptimal solvers that can compute high-quality solutions. And how many agents they can navigate? Usually hundreds. Still not good enough. And we found there are also some of the solvers, they claim they can compute solutions for thousands of agents. But if we look at them, I can tell you their solution quality is far from good. So we propose a new method that can compute high-quality solutions for thousands of agents and return the solution in short time. Our method can turn infeasible solutions to high-quality solutions through a repair and improve process. And experiments showed that our solver achieved high success rate on benchmark set with more than 800 problems. And each of the problems have more than 1,000 agents. If you want to look more about this work, and you can find our poster for details. Thank you.